So now the procedure for converting a regular expression to an NFA is called the Thompson construction. Okay, Thompson construction. So this is not the physicist. This is not the physicist Thomson. So there is a physicist with last name Thomson. I think without a P. So that's a physicist. This is a computer scientist. Okay. So the idea here. So let's ask this question. Suppose that we have a regular expression. You know, we know how to construct a regular expression, an NFA for a trivial regular expression. You know, for example, if you have a regular expression that consists of a single letter in the alphabet. So suppose our alphabet is AB. So this is an NFA, a trivial NFA that will accept A. So this is an NFA for the regular expression A. So A is a regular expression. That consists of a single symbol, right? In general, what's a regular expression? A regular expression consists of the symbols of the alphabet, related using 3 operations. What are the 3 allowable operations in a regular expression? 3 operations. So yeah.
0 or more, 1 or more.
But what are the operations in the regular expression? What are the operations that we apply to the? Yes.
Union,
yeah.
Concatenation, and repeat.
Exactly. Union, concatenation, and star. Or the clean closure. It calls clean closure, but let's call it star, which is repeating. So these are the 3 operations, which we call regular operations, by the way. So a standard regular expression can have can have any combination of these operations, but it cannot have any other operations. Anything else is an extension of the notation of regular expressions. Now, if we know how to construct NFAs for the individual symbols, just like this, it's trivial, and we know how to construct, given 2 different NFAs for 2 different languages, we know how to construct an NFA for the union, and how to construct an NFA for the concatenation, and how to construct an NFA for the star, then we are done. Then we can build an NFA for any language. So these are the building blocks, and these are the operations that we apply to these building blocks. Then we can build an NFA for any general regular expression, as we will see. At the end we will give a complete example, and things will not become 100% clear until we get to the complete example. Okay, so now suppose that I have 2 NFAs. So this is NFA 1, and this is NFA 2. So I have 2 NFAs for 2 different languages, and I would like to construct an NFA for the union. Now, the question is, can I assume, without any loss of generality, that an NFA has a single accept state? Is this a valid assumption or not? That every NFA consists of or has a single accept state?
No.
Well, it may sound, on the surface it may look like we are losing generality by making this assumption, but in fact we are not losing generality. Why? I can assume without any loss of generality that every NFA has a single accept state. Why? Yes.
So you can just map every accept state into a new accept state.
Exactly. Exactly. Because if you have an NFA with 1,000 accept states, with many accept states, you can just do this. You can just have an epsilon transition to one accept state, and then you make these regular states. So these, you change this to a regular state, you change this to a regular state. So if an NFA has many accept states, you can map this to an NFA, or you can convert it easily to an NFA that has a single accept state by doing these epsilon transitions from the existing accept states to a new accept state that you introduce, and then you change these from accept states to regular states. Okay. So now, given this, we can assume without any loss of generality that an NFA has a single accept state. Now, to build an NFA for the union, what should we do? The union of these, this is an NFA for language 1, this is an NFA for language 2. So this is for language 1, this is for language 2. So we need an NFA for L1 union L2. Yes?
We use a branch.
Yeah, so we branch. So we have a start state, then we branch. Okay, so we branch, and this is the, this is NFA1, and we have this accept state, and this NFA2 with this accept state, and then what should I do? I don't have accept states now. Well, I can leave it like this, by the way. I can leave it like this. But to stick to our standard of having one accept state, we can just map these to one accept state. We don't have to, by the way. So this is correct. This is correct. We don't have to map them to one accept state or introduce a transition to one accept state. But let's stick to our standard of unifying the accept state. So this is an NFA for the union, right? OK, so this is for the union. For the concatenation, NFA for the concatenation, let's do it here. NFA for the concatenation. So what should we do? For L1 concatenated with L2? Yeah, exactly. So put L2 after L1. So we just do this. OK, I will do something wrong. Then we'll figure out what's wrong. So NFA1, NFA2. OK, so this is an NFA for the concatenation, L1 concatenated with L2. So what's wrong with what I have on the board?
In NFA1, that should no longer be an accept state.
Exactly. So this accept state, I just did this to emphasize that when we do the concatenation, the accept state of the first NFA will no longer be an accept state. Just to emphasize this. OK? We are doing the abstract now, but in a minute we will see a concrete example for this. OK, so this is the concatenation. Now let's do the star. The star is a little bit tricky, so let's do an NFA for L1 star. So an NFA for L1 star, let me do the, make a first attempt that will be wrong, and then we'll see why it's wrong and how to correct it. So if I do this, this is NFA 1. So to construct an NFA for the star, what will be tempting is to do what? To do epsilon from accept to start, right? You'll be tempted to do this. But in general, this will not work. Because, first of all, for a star, you have to accept the empty string all the time. Because star, you can repeat 0 or any number of times. And if you repeat 0 times, this means the empty string. So you have to accept the empty string. So this will not necessarily accept the empty string. But if we try to accept the empty string by doing this, then this will be a disaster. Right? Why will this be a disaster?
We'll never get to the other one.
Oh no, we are assuming that we are not changing what's in between. So NFA1, we are assuming that all the transitions that are in between the start state and the accept state, they're the same. So in this case, we can have a million states between them, and they are still the same. So all the transitions and the states between the start and the accept are still there. We don't touch them. This is what I mean here. So it's good that you brought this up, because I'm not implying here that my NFA consists of 2 states. It consists, this is the accept, this is the start, this is the accept, and between them you can have as many states as you want and as many transitions as you want. But we are only looking at the start and the accept. Okay? So yeah, I'm glad that you brought this up. So okay. So now, why is this a disaster? Yeah.
If you have in the NFA, if there is a return to start, that would be intended to be an error. That you're not supposed to accept it, but since you've just turned your start into an accept state, it would still accept it.
Yeah, it will accept many things that shouldn't be accepted. And the easiest, the simplest example, what if the state has something like this? 0, 1, or sigma. Sigma, assuming that sigma equals 0, 1. So if it has this, if the original NFA has this, then what are we doing here? What's the language that this NFA recognizes? What does this NFA recognize now with everything in red?
Zeros and ones.
Well, it's going to accept anything which is sigma star. So it's going to accept any string. Any string will be accepted because you are already in an accept state and you have a transition. So let's give a concrete example. Let's give a concrete example. This is abstract. So what if we have this language L, the set of strings W such that W ends with 1. So ends with 1 is going to be, the NFA is going to be like this. 0, 1, and then if you have a 1, you are in an accept state. Right? So this is an NFA for this language. W ends with 1. Now if you try to construct a state for the star, for L star, by doing this, right? Then this is no longer this is not the star of this. This is an NFA for sigma star. This is an NFA that can accept any string because this is already an accept state. Okay? So in conclusion, I can't use the existing start state as an accept state that will allow me to accept epsilon. So I'm going to introduce a new state, a new start state that I will make accept state. So now this is so I will introduce a new start state. This will become an accept state, and I'm doing this only to accept epsilon. But this will not accept anything. And then the transition from I have to have this backward transition from the accept to the start to implement the loop, the repeating. And then to stick to my standard of having one accept state, I will let me just draw a new one. So I will just do this. So this is NFA 1, and then and then both of these are going to go to one accept state, and of course these are epsilon transitions. Okay, so this is how I construct an NFA for the star. I introduce a new state, and then I add an epsilon transition from the accept state to the start state, and both of these, the existing accept state and the new accept state, I introduce a transition from them to a new accept state. Yeah.
Would we be able to use the new initial state as the accepting state? I don't understand why you created a second new state.
You can, but it's just to be systematic. Systematically apply the same procedure, maybe to make it emphasize that these were the two original accept states, and we mapped both of them to one accept state. Okay. Yeah, so you are suggesting using this as one accept state and then mapping, introducing an epsilon transition from this to this? You have to think about this. I can't verify it now. I will have to think about it for a minute. It may do something wrong. So I'll need a minute or two to think about it to verify that this will work. But I'm sure that this works. Okay, so now this looks abstract. Now let's look at a concrete example, and the concrete example will look much easier. Okay. So let's do a concrete example from the book. A, B union C star. So this is a regular expression, and we would like to construct an NFA for this regular expression. Okay. So we first construct regular expressions for the individual symbols, which is trivial. So this is a regular expression for A is going to be A. And a regular expression for B is going to be B. And a regular, sorry, NFA, not a regular expression. Sorry, I meant an NFA. NFA for C is C. Okay, so this looks trivial so far. Now what should be the next step? Constructing an NFA for, so if you were evaluating this expression, what would you evaluate next?
Inside the parentheses.
Yeah, the union. So the next step is to construct an NFA for the union. So an NFA for B union C. So using the rules that we just had on the board, constructing an NFA for the union, we will just branch, right? So we will do this, epsilon, epsilon, and then this is B, and then this is C. Then what?
Just go to a common accept.
One common accept state. And again, having one common accept state is not necessary, but let's stick to this convention or standard. It's not necessary for correctness, but let's stick to this convention. Okay, so now we have an NFA for B union C. Now we need to construct an NFA for what? Did you have a question? So an NFA for the star of B union. So we have to star this whole thing, right? So this is going to be the main step here, starring this whole thing. And starring, we will have an epsilon transition to the start state, and we will introduce a new state. So let's draw a new one. So NFA for B union C star. So to star something, we add a new state. Let's do it in a different color. And then we copy this whole thing. We just copy. Well, I'm copying right now. Okay. What else do I need to do? What else do I need to do? What's the most important step in the star?
You have to go back to the beginning.
Yeah, you have to go back to the beginning. Okay. So I did this. And now my accept states are this and this. So I will just add this, or let's make it look better. Okay, so this is an NFA for B union C star, or the star of B union C. Oh, and I forgot these. Okay. Now what remains is what? What's the last step?
Adding A.
So concatenating A with this. And concatenating means just you stick the A before this. So I'm not going to draw this again. I will just put the A. So this is the A. And yeah, so the A is going to get connected to this using a star, an epsilon. So I connect them with an epsilon transition. And the accept state for the A will no longer be an accept state. Remember, the accept state for the first one will no longer be accept. Now, the obvious observation here is that this procedure introduces too many what?
Epsilon state.
Too many epsilon transitions. So we will do it systematically. So because this is something that we will program. Programs process the input systematically. Now, there are ways of minimizing the number of epsilons, but you have to think of it of a systematic procedure for minimizing the number of epsilons. So it's not always obvious whether a certain epsilon transition can be eliminated or not. Sometimes some of them are redundant and can be eliminated, and some of them can't. So it's not a trivial task to determine which of these stars are redundant and which ones can be eliminated. So we will stick to the systematic procedure that may sometimes introduce a ridiculously large number of epsilons, but we will stick to the systematic procedure, the Thompson procedure. Okay. Questions? Okay. In fact, this is one of the topics that usually students find very easy. So in the exams, in theory of computation, in compilers, I may or may not ask about this in the exam, but in theory of computation, I always have a question like this, and students usually find it very easy because it's very systematic. Yes?
So when these questions are asked, we are going to be expected to have these epsilon transitions?
Yes, yeah. So just do it systematically. Because in fact, in this course, we care more about doing things systematically because we are building a program. And the program, a program may not be as smart as you are when you look at this on the board. When we look at a small example on the board, we can identify redundant epsilons, or we can find a way of minimizing the number of states. But to do this in general is non-trivial. To do it for, imagine a state with an NFA with 1,000 states. So it will not be easy.